Hi, my name is Emily. I'm a PhD student at the London School of Hygiene and Tropical Medicine, where I work with Rachel and Adam Kucharski. And today I'm going to be talking about disentangling the role of climate and immunity in driving dengue outbreaks in Singapore. So briefly, a bit of background about dengue virus. Dengue virus is an arbovirus. It's transmitted by Aedes mosquitoes, principally Aedes aegypti and Aedes albopictus, which causes an estimated 100 million symptomatic infections a year alongside 10 million deaths. And as Rachel mentioned earlier, around half of the global population are thought to be at risk of dengue transmission. Most infections are asymptomatic or mild, but it can develop into a flu-like illness known as dengue or severe disease known as severe dengue. What complicates the epidemiology of dengue is that it exists as 4 immunologically distinct serotypes, named dengue 1 through to 4. An infection with one serotype provides lifelong serotype-specific immunity, but only short-lived cross-immunity to the other serotypes. So it is possible to be infected multiple times with dengue with these different serotypes. So moving on to dengue in Singapore. Singapore is a city-state. It's hyper-endemic for dengue with year-round transmission, and Singapore has experienced above zero case counts of dengue every single week for the past 20 years. And here I've shown the time series of weekly dengue cases in Singapore from January 2020 until January 2000 until January 2020. And in addition to this, since dengue re-emerged in Singapore in the 1980s, Singapore has experienced outbreaks of dengue with an epidemic cycle of around 5 to 6 years. And these have been increasing in frequency and magnitude over time. And I've highlighted here with the shaded bars some particular outbreak years. And a key question for early warning systems is to predict when these outbreak years might occur and how bad they may be when they do. And there are several ways that we can think about this issue. The first is to look at climate drivers. So as an example here, I've plotted the same weekly dengue case count over time. And then below it, I've put the Niño 3.4 index, which measures sea surface temperature anomalies in the Pacific Oceans. And this is the 5-month running average. So this is used to define El Niño and La Niña events. And you can see that that these sometimes temporally coincide with particularly bad outbreak years. So for instance, you can see that in 2016. Another element that's important to consider in the Singaporean context is switches in the dominant serotype. So most years, all 4 serotypes are present in Singapore. And here I've plotted the prevalence of each serotype alongside the same dengue case count as before. And what you can see here is that every so often there will be a switch in the dominant serotype, and often this then leads to a large outbreak of dengue because this is changing the immune profile in the population, and people may not have as much immunity to the new serotype. And you can see this, for instance, in 2007 when there was a switch from dengue 1 to dengue 2 as the dominant serotype, followed by a large outbreak. And then you see the same pattern again in 2013 and 14 when you had a switch back to dengue 1 and this large 2-year outbreak. A quick note on climate in Singapore. Singapore has a tropical climate with consistently high temperatures, rainfall, and humidity all year round. Precipitation peaks between sort of November and January, and highest temperatures are seen around May and June. And then the typical dengue season in Singapore runs between June and October. So our overall aim with the study was to quantify the relative role of climate and serotype switching in shaping dengue outbreak risk in Singapore over the past 20 years. And this is broken down into several questions. So firstly, I wanted to investigate what the relationship was between the climatic variables of interest in dengue cases and how do these vary at different lag times. So by that, I mean the relationship between a climatic variable such as precipitation and dengue cases might be different if you're thinking about precipitation a month ago or 4 months ago. Our second question was, what is then the additional benefit of adding serotype information into this climatic modeling framework? And then thirdly, we wanted to look at whether these could be combined into an early warning system model framework that could give advanced warnings of dengue outbreaks in Singapore. So the modeling framework that we used a Bayesian hierarchical modeling framework based on the following equations. So dengue case counts are assumed to follow a negative binomial distribution, and then the log of the dengue incidence rate can be explained by a linear combination of population offset, climate and other model covariates, and some random effects. And these are broken down into a yearly random effect, which aims to explain variation due to kind of long-term annual changes. So this might be like a vector control campaign or a change in reporting, something that we're not including in the model that's changing at that sort of annual scale. And then a weekly random effect, which incorporates seasonality in the data. And we're investigating several climate variables that I list below, and we're considering each of these variables at a time lag from 0 to 20 weeks. Another method that we employed in the study was we looked at distributed lag nonlinear models. And these are a very useful way of understanding the full picture of this exposure lag response association between dengue relative risk and the climate indicators. And this can be visualized with these contour plots, and I've shown some here below from one of Rachel's paper, where you have the climatic exposure on the y-axis and then the lag on the x-axis, and then the color and the intensity of the color shows to what extent this particular exposure lag combination influences dengue relative risk. And these can be used as predictors in the Bayesian modeling framework. So we did this looking at the data that we had for Singapore, and we found some quite interesting patterns. So for temperature, here I've shown maximum temperature, and with these plots, green is a decreased dengue relative risk and purple is an increased risk. So here we found an interesting non-linear relationship between temperature and the risk of dengue. And this holds for most lags where low maximum temperature and high maximum temperature both decrease your risk. So it gets too hot for transmission at some points in the year. So here I've shown the same type of plot, but for cumulative precipitation, where we found a simpler relationship where increased precipitation at most lags decreased the risk of dengue incidence. And then finally, we found a very interesting pattern with humidity, whereby the effect of absolute humidity on dengue risk actually depended on the lag that we considered. So thinking about like a long lag time, so thinking about humidity 5 months ago, we found that high levels of humidity, so very humid conditions, decreased the risk of dengue, whereas low humidity increased the risk of dengue. And then we found this pattern was reversed when we consider short lag time, so at the left of the graph, where we found that high levels of humidity recently increased the risk of a dengue outbreak and low levels of humidity decreased dengue risk. So we wanted to take these insights to build a simpler climate model that might be more practical for an early warning system type framework, but keeping these insights that we found. So we wanted to incorporate this non-linear effect of temperature and this differing effect of short and long lead humidity into our model. And on top of that, we also wanted to include some information about serotype, and we thought about different ways of doing this. So we tested including the prevalence of various serotypes, which serotype was dominant, and also testing the time since the last serotype switch. And then we conducted model selection using various criteria, including the WAIC and the cross-validated log score. And so here are the results of that model selection process, where we compare models of increasing complexity. So the first model shown is a baseline model where we only include those random effects that I mentioned earlier, the seasonal and the interannual random effects. Then the middle model, the second model includes those random effects, but also the climate covariates. So the optimal climate model, which the covariates for which are listed below. And then the third model includes both climate and serotype switching. And we found that this was the best performing model by both the WAIC and the cross-validated log score. So here I've plotted the observed dengue cases in green and the model predictions for median dengue cases in purple and the 95% credible interval in the purple, lighter purple color around it. And you can see that the model is able to fit the data pretty well. Also, for comparison, it's a little bit difficult to see, but the black line shows the random effects only model, so you're able to see particularly where in that time series adding the climate and the serotype information is helping. As well as improving model fit, we were also interested in understanding how including serotype in our model was helping to explain the variation in our data, and particularly this interannual variation, which is really important for understanding which year we might have a particularly bad dengue outbreak in. So here, and the way we did this was by looking at those annual random effects that I was mentioning earlier. And so here I've plotted the estimated annual random effects for each of those three models I mentioned. So the random effects only model, the model with climate, and the model with climate and serotype. And this is useful to look at because the closer that this random effect is to zero, the more of the interannual variation is being explained by other elements of the model. So being explained by either that climate information or that serotype information. And you can see that for quite a few years, the model with serotype in it is clearly explaining a lot of this interannual variation. So for instance, here in 2007 and 2008, the green line, which is the climate and serotype model, is much closer to zero. And then again from 2013 till 2016, which suggests that the addition of this serotype switching variable is helping to explain some of this intraannual variation in dengue incidence that we're seeing, which is promising for its use as a predictor in an early warning type model. So in conclusion, then, we found so far that the relationship between climatic variables and dengue incidence in Singapore is complex. We found evidence of a non-linear impact of temperature and of differing effects of short and long lead humidity. And we found that incorporating serotype switching into a climatic modelling framework helped to improve our model fit and explain our interannual variation in dengue incidence. And our next steps with this work will be to evaluate the out-of-sample predictive ability of the final model. Thank you very much for listening.